Okay, so this is now on polynomials. Polynomial is an x to the n plus a minus 1 x minus 1 plus blah, 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 blah. It's basically a bunch of x's raised to positive integers multiplied by numbers. That's called a polynomial, and the leading term is the one with the highest power. And you can also factor them, and we will get into that next week, how you factor these things. But here we want to draw graphs of polynomials, and there's two things we need to do this. The leading term, that's this thing, which determines the end behavior, and you need all the factors if you can get that, which is all the x-intercepts. So what does the leading term tell us about the graph? Well, the leading term determines the end behavior of the graph of the polynomial, and the end behavior is what the graph looks like for very large positive x and for very large negative x. And so here I'm going to try and splice in a video from GeoGebra trying to explain some of that.
Okay, so we want to talk about what end behavior means. And so I've got two functions here. The green function is this thing, and the blue function is just the highest powered term of the green function, right? So it's just the x to the fifth. And they look very different, but notice that we're only looking between x is minus 4 to 4 and y is what, minus 6 to 6. And it looks like as we get to the left and the right, they go in the same direction. So what we can do is we can zoom out by changing the settings, playing with the settings a little bit. We'll put our x-axis to be from, let's see, minus 10 to 10. And we'll put our y-axis to be from, minus 100,000 to 100,000. Minus 100,000 to plus 100,000. Maybe we should actually make this minus 30 to 30, just to make that a little bit bigger. Great. So what we saw at when we were zoomed in pretty close was that the green function, which is this thing, it actually did a little wiggle in here, and the blue function didn't. The blue function just did this. But if we zoom out on a really big scale, right, and notice how big the y numbers are, the two graphs look pretty much the same. So what we can tell is that if we just look at the first term, the x to the fifth term, we can tell something about the shape of our graph. It's got to look like x to the fifth, the first power, the first term, for a very large x. That's called the end behavior. So the end behavior of this function, of f, the green function, is the same as the end behavior of g, the blue function. All you have to do is look at the first term. So both functions go up to the right and fall down to the left. If there was a negative term, right, that would just switch it. But you still see the match between the function and its first term. Now the first term is minus x to the fifth. So with a minus sign and an odd power, you go up to the right and down to the, up to the left and down to the right. Okay, so similar thing happens if you have even powers. Here's a function. The red function is 3x to the fourth and a bunch of different things. It's got a bunch of x-intercepts. It goes down, up, and down. The, I guess that's purple function, is just the first term. And if you notice, right, they both go in the same direction. The red and the blue, purple go off up that way and up that way, even though the red term bounces around it a bunch. So we can do the same sort of thing here. If I can get my settings correct. We'll just zoom out by changing the x coordinate to minus 10 to 10. And the y coordinates from, well, y doesn't go, the graph doesn't go below minus 10, so we'll just leave that at minus 10, but up to 10,000. Right. And there's our graph. I'm going to zoom out a little bit. So they're not exactly the same, but the two graphs, the red and the blue, both go off in the same direction. So the red graph pretty much tracks its leading term as long as x is pretty big. Right, and so 3x to the fourth, it's an even power, so we go up to the left and up to the right. It's positive and even. If it's negative, well, that'll flip it over the x-axis. Right, and if this is x to the fourth, no matter what x you plug in, that's going to be positive. So minus 3x to the fourth, that will always be negative. And so that will give me a graph that looks something like that. So what we see here then is that the leading term of a polynomial tells you what's going on for pretty large x. In this case, actually, x is just bigger than minus 8 or 8. In here, in the center, right, it wiggles up and down a little bit. But as you get away from the x-intercepts, the function just follows its leading term, its highest term.
Okay, so having seen that, we get four basic shapes for our end behavior, and they depend on the sign and whether or not the power is even or odd. So if the power of leading term is even or odd. So I'm going to draw a little table here. So even power, odd power, positive leading term, and negative leading term. So what does an even power with a positive leading term look like? It goes up on both sides. The negative leading term, right, it's just a flip of that. It goes down on both sides. So even powers, right, a negative number raised to an even power is positive. So that'll give you a positive for negative x's. If you throw a minus sign on it, it would just flip it over. Odd powers go up to the right and down to the left with a positive sign. If the power is odd, but we have a negative sign, it goes down to the right and up to the left. Now remember that by thinking odd means I get opposite behavior. One side goes up, one side goes down. Even, I get same behavior, both sides go up or both sides go down. Okay, so that's the end behavior. The second thing to look at after the end behavior is the x-intercepts. And what happens at the x-intercepts depends on what the power of the factors are, right? Every x-intercept corresponds to a factor, but the factors can have powers on them. So I'll splice in another little video here from GeoGebra to talk about powers and what they do to a graph.
Okay, so we want to talk about what these terms here, these factors, have to do with why this graph goes through the x-axis here, but only touches it there. So this is just a point on the graph, a comma f of a, and if we let a vary, it goes to the left, and then as a gets to -2, it'll come back up and swing to the right. It just traces out a curve along our function. We want to pay attention to the y values on this thing. So we'll stop for a second. We bring our x values, right? -1.3, this is an x value. If it's less than -1, we have a negative y value below the x-axis. If we bring it up past 1, we have a positive x value. If we actually set it exactly equal to 1, which is a little tricky, but there you go, it's sitting on the x-axis. So where are the x-intercepts? 1 is one of them. and that makes this factor here equal to 0. This factor here, that's equal to 0 when x is equal to -1. So that's our two x-intercepts, +1 and -1. So why does it touch the graph at x equals 1 and go through the graph at x equals -1? Well, that has to do with the powers on our factors. So note that this is a power squared. So this term is always going to be positive because anything squared is positive. This term is to the first power. An odd power, if you have a negative number raised to an odd power, you get a negative number. So when we're looking at this behavior right around -1, if x is a little bit less than -1, so our x here is -1.1, it's a little bit left of -1. This term here is negative, and negative raised to an odd power is negative. This term here is also negative, but it's a negative squared, so this is positive. So what do we have? We have positive times negative, that gives us a negative. If we go past -1 to say x equals -0.9, then this term is now positive, right? Because -0.9 plus 1 is positive, and this term is still positive. So we get a positive times positive, and we're greater than 0. We're above the x-axis. So a y value greater than 0 means we're above the x-axis. So what happens? So what happens here, because that's an x plus 1 to an odd power, is you change signs, right? You go from negative to positive. What happens here at 1? Well, if x is close to 1, this is always going to be positive. The x minus 1 squared, that's responsible for the x-intercept right around x equals 1. But this never changes sign. It's always positive. So as we go from left to right, both terms are still positive. So it dips down, touches the x-axis, because this term is equal to 0, and then it bounces off the x-axis and keeps going up because it's all still positive. So odd power, you go, if your factor has an odd power, you go through the x-axis. If your factor has an even power, you touch the x-axis.
And so suppose we want to look at this graph and we want to find the end behaviors. So this is y equals 2x to the 7th plus 8x to the 6th plus 8x to the 5th. And we want to know, what does this graph look like? Well, the first thing we want to do is the leading term. I think my math lab calls this the leading term test, is 2x to the 7th. This is odd power, and it's positive. So its end behavior looks like this. So our graph is going to do something in here, but it's going to end up going out that way and going down that way. It's going to do something in between. So how do we figure out what it's going to between? Well, then we want to factor. So how do we factor this thing? Well, we look and see what's the highest, the biggest thing that's in common to all three terms that I can factor out. And there's an x to the 5th that I can factor out of everything, and there's a 2 that can be factored out of everything. So I have 2x to the 5th. If I take a 2x to the 5th out of 2x to the 7th, I'm left with an x squared. If I take a 2 out of an 8, that gives me a 4. If I take an x to the 5th out of x to the 6th, I've got 6 x's. If I take out 5 of them, I'm left with 1. And if I take a 2 out of an 8, I'm left with a 4. And if I take out all 5 x's, I'm left with a 1, which just gives me that. And I can recognize this as being a perfect square. It's x plus 2 quantity squared. Great. So factors, x to the 5th and x plus 2 quantity squared. Power is 5, which is odd. This is 2, which is even. So, as we saw in the video, if you've got an odd power, you go through the x-axis. If you have an even power, you touch it. What are the actual x-intercepts? Well, if we take the factors and set them equal to 0, that's where we figure out what the x-intercepts are. So x to the 5th equals 0. Well, that means x equals 0. X plus 2 squared equals 0. When is that equal to 0? Only for x equals minus 2. So those are my two x-intercepts. So minus 2 is an x-intercept, and 0 is an x-intercept. And power here is 2. So that means I touch at minus 2, because that's the factor that we're dealing with. Power on the x to the 5th is odd, so we go through at x equals 0. So the graph starts with its end behavior here. It'll touch there, go through there, and end up going out there. And so there's the graph of a polynomial. So the factored form of a polynomial looks like this. The powers on a factor is called a multiplicity, these things. So the multiplicity here is 5. Multiplicity here is 2. The numbers inside the factors, these numbers are called the roots or the zeros of that. And if the multiplicity of a factor is even, you touch the x-axis, like there, but does not go through at that. And I should have had here, if the multiplicity is odd, graph goes through the x-axis. So this thing, sketch the graph of that thing. What does the graph look like? Well, we can handle that now. We have to find the leading term in the end behavior, find all the x-intercepts and the multiplicities, and whether the graph goes through or touches it, and then we sketch the graph. So we'll do this on this next page. There we go. And we will say, we'll just write down the equation again. Y equals minus 3, x minus 2, x plus 3 squared times x plus 1 cubed. What's the leading term? Well, you need this. The leading term is, if you multiplied all this out, what's the highest power you'd get? And if you multiplied them all out, you'd have the minus 3, so that has to go along with it. If you multiplied everything out, you'd get 1x from there. You'd get an x squared here when you FOILed this out. You'd get an x cubed from there when you FOILed it out. So you'd end up with x times x squared times x cubed, which is x to the 6th. The thing to remember here, to get the power of the leading term, just add up the powers on all the factors. 3 plus 2 plus 1 is 6, so it's minus 3 to the 6th. So it tells me what my graph looks like. Even power with a minus sign, that means my end behavior looks like this. So I can list all my factors. I've got x minus 2, x plus 3 squared, x plus 1 cubed. So what's the x-intercept that goes with that? Well, you set these each equal to 0 and solve for x. And it's really actually pretty straightforward. Here, x equals 2. Here would be x equals minus 3, right? Because if you said x equals minus 3, this thing in the parentheses is 0, and this is x equals minus 1. So the multiplicity is the power, and what we're really interested in is it even or odd. So the power here is 1, so that's odd. The power here is 2, so that's even. The power here is 3 is odd. And that asks us, does it go through or does it touch? So an odd multiplicity you go through, and an even multiplicity you touch, and an odd multiplicity you go through. Great, so we have all our information that we need. X-intercept of 1, 2, 1, 2, 3. We've got an x-intercept at minus 1 and at minus 3. At x equals minus 3, that's here. It's even, so you touch. So you come up from here, touch the graph there. When we get to minus 1, you go through. And when you get to 2, it's odd, so you go through again. And then you hook up with the end behavior. And so there's the graph of that function. When we're graphing these things, what we're really interested in is which part of the graph is above the x-axis and which part of the graph is below the x-axis. We're not really worried too much about exactly what the scales are, right? How high up this goes or how far down that goes. Be a little bit careful about graphing these things on either graphing calculators or in GeoGebra, because if your scale isn't right, it can look really strange. So in the video, the GeoGebra video, I showed you how to change the scale on the axes. And sometimes you need to do that if you want to check your answers there. So what about this one? Following the steps above. So leading term, well, there's no coefficient out here, so that's just a 1. 3 plus 2 plus 2, that's 7. So the leading term is x to the 7. That's odd power and positive. So that means we know what the end behavior looks like. It looks like this. X-intercepts, 4, minus 2, and 1. And I get that just by looking at these three things. X minus 4, if I set x equal to 4, that makes this thing inside the parentheses 0. If I set x equal to minus 2, that makes that inside the parentheses 0. If I set x equal to 1, that makes that inside the parentheses 0. And then I want to know the multiplicity. The 4 came from this term, odd multiplicity, right, because it's a 3. The minus 2 came from this term, that's an even multiplicity. And the 1 came from this term, and that's an even multiplicity. Odd means you go through, even means you touch, even means you touch. So, minus 2, 1, and 4. So there's my x-intercepts, and minus 2. So we come from our end behavior, we touch at minus 2, and then the next one is 1. So we touch again, and the next one is 4. And then we go through, and we hook up with our end behavior. And so there's the graph of that polynomial. So graphing polynomials, if they're factored like this, isn't too hard. You figure out the leading term. The power is just adding up all the powers on all the factors. And then each factor will give you an x-intercept. Figure out what the multiplicity is, whether it's even or odd, and you can figure out whether you're going through or touching.